and Human Values, Bharatiya, Bhavan, Bangalore, and also the Honorary Professor at National Institute of Advanced Studies, Bangalore, India. He retired from National College, Bangalore as Principal and Professor of Mathematics after 35 years of service. A researcher in history of astronomy, particularly Indian astronomy, he has completed projects on Indian astronomy under the Indian National Science Academy, INSA, New Delhi, and published quite a few books, research papers, and popular articles on Indian astronomy. Currently, he is working on Indian astronomical tables vis-à-vis European astronomical tables. Let me now request Prof Balachandra Rao to make his presentation on three contemporary astronomers of the early 16th century, Nīlakaṇṭha Somayājī, Gaṇeśa Daivajña, and Copernicus, a comparative study.
Respected scientists, scholars and friends, I shall try to make a presentation before you by the way of some glimpses of a comparative study of three contemporary astronomers of the early 16th century, as mentioned in the title. They are obviously Copernicus from Poland, then two Indian astronomers. One is from Kerala, Nīlakaṇṭha Somayājī, and the other originally from Maharashtra, Gaṇeśa Daivajña. Why we have personally have chosen these three astronomers is that all the three, in our opinion, made great breakthroughs in the field of astronomy in particular. Of course, Copernican theory of heliocentric motion of planets is considered a great breakthrough in physical sciences, and he has been explored for all the remarkable contributions he made. Until Copernicus, world over, geocentric theory was adopted for computations of planets, eclipses and the rest of it. And that worked reasonably well for a long time. And we do give credit to Ptolemy for systematizing this geocentric model of the planetary motions, as also the mathematical procedures, and where necessary or possible, even the geometrical proofs, because these Greeks were obsessed with the geometrical proofs, as pointed out by Professor Gabritis in the morning. And unless something is given geometrically acceptable, they would not deem it as a mathematical theory or mathematical procedure at all. That was the practice in Greece. But in contrast, in civilizations like our own, or Chinese, or Babylonian and related civilizations, the approach was totally different. It was more computational, result-oriented, and it is argued by some of our top scientists that this computational and result-oriented approach, adopted by Indian astronomers in particular, as also by Babylonian astronomers earlier, this has an advantage over the Greek obsession with geometrical deductive proofs. And we know from history of science that the Greeks had the disadvantage of not crossing the barriers of their obsession with geometrical symmetry and the rest of it. As most of you might be knowing, Greek geometers were familiar with the conic sections, parabola, ellipse and hyperbola. Apollonius wrote a monograph on the conic sections. Then, as modernists, we wonder, why on earth could they not think of the possibility of planets moving in an orbit other than circular? They could have easily thought of either ellipse or parabola or hyperbola with which they were familiar, but they could not. So they managed with circles only, too many circles for that matter. And even Copernicus failed to recognize this fact. And Copernican theory, though it is considered a great breakthrough in physical sciences, in shifting the center of the solar, what we call solar system, from the earth to the sun, that was indeed a great achievement in the history of science. But if you go into the procedures recommended and adopted by Copernicus, nothing is really that rewarding. And we have been working on his text De Revolutionibus, page to page, word to word, and also the geometrical proofs, etc. he has given, and the observations he has recorded. And there we find a great lacuna. While principle, his heliocentric model is certainly a great achievement over thousands of years. But practically when it comes to computations of planetary positions or eclipses and the other astronomical phenomena, it is not at all adequate result producing text at all, de-revolutionaries, for various reasons. And Neugebauer and Swardo, who have written a mathematical analysis of his de-revolutionaries, keep on harping on the point that Copernicus is a failure here, for various reasons. One reason is maybe psychological or emotional. He continued to be too loyal to Ptolemy. Whenever his so-called heliocentric results of observations or computations tallied with Ptolemaic theory of computations or procedures, he used to feel very happy. I mean, that is very explicit in his text. And whenever his results based on his own heliocentric theory differed from Ptolemy's results, he would feel guilty. So there was some peculiar psychological things going on in him. And of course, the hold of church, medieval church, could have also been responsible. We are told that this Copernicus was hesitant to announce his heliocentric theory to the world at large. It was only for private circulation. He often interacted with some fellow astronomers, and whenever the church entered into the matter, he tried to convince them, saying that geocentric theory is the real theory, and this so-called heliocentric model I am trying to work out is only for mathematical convenience. This is the sort of course we don't blame him for that. Anybody that in his position perhaps would have been like that. So all the same in his text, he could have been more bold in getting results which are in conformity with his heliocentric model. Of course, the deficiency of his model was that he propounded a heliocentric model in which all the orbits are concentric. Of course, they are not coplanar. That is one small concession he made. Otherwise, it would have been still worse. So, concentric circles he took. With that, obviously, he could not manage to get the result because planets do not move with uniform angular velocity in a circular orbit. So, of course, mechanics had not seriously developed by then, and the concept of force itself was not there. Only by kinematic constraints, kinematic conditions, and the wonderful geometry they had available to them, and based on observations. All these things have to be developed. To that extent, we do congratulate Copernicus and his predecessors, because in the absence of proper mechanics, all they could do with only observations and geometrical manipulations, that is something really a great achievement from our point of view. But then, coming to India, because it's interesting and quite rewarding to make a comparative study. Here also in Indian system, of course our value system is totally different from those of either Greeks or Babylonians and others. So we have to take that also into consideration. Why Indians were that much obsessed with the planetary positions, eclipses and the new moons, full moons, because of their religious preoccupations mainly. And that is something which distinguishes, I think, India or ancient India from the rest of the world. And this had its own impact on the development of sciences in this country, sometimes for the good, sometimes maybe for the bad. So it went on like that. So, but there were positive developments in a subject like astronomy, thanks to the religious preoccupation of the ancients here. And I may come to those points now and then. Well, making a comparative study, I was telling. So, coming to Indian astronomy, there was a great breakthrough in that period, thanks to two great astronomers. One is obviously Nīlakaṇṭha Somayājī of Kerala. And this morning, Professor Devarkis made a comment that he has been speaking of Kerala mathematics for the past 25 years, and he wanted a break. But we are just entering into Kerala astronomy. And it is a pleasure to study the Kerala contribution to astronomy in particular. Mathematics we have been mostly familiar with. Astronomy in particular, how it differed from the development in the rest of the country. Thanks to Bhaskaracharya, the first and the second, Brahmagupta, Aryabhata and all these people. Compared to them, the development of astronomy in Kerala is something truly unique. And personally I have been working in that field And as was pointed out in introducing me, currently I am working on astronomical tables, because for actual observations of the heavenly bodies, as also for computations of our Indian traditional almanacs, the Panchangas, the tables are used. The texts proper are not used. Take, for example, a text treatise like Surya Siddhanta. Shlokas are given, methods are given, procedures are given, parameters are given. But the Panchaga maker does not use the text as it is. He does not take shloka by shloka, translate and all that. He depends on ready-made tables. These tables are, they are called koshtakas, sarinis, and then such words are used. These tables are available in Sanskrit, in our local languages like Kannada, Telugu, and Malayalam, and all these languages they are available. They are based on some earlier or ancient treatises like Surya Siddhanta or the Siddhanta Shiromani of Bhaskaracharya or Brahmasputra Siddhanta of Brahmagupta or Gaṇeśa Daivajña's Grahalagavam. Like this, these are the basic texts. Based on these tables are followed, and I am into those tables now, comparing them with the available French tables and other European tables, because there is a reason why we make such a comparative study. An often made Western criticism from scholars is that these ancient and medieval Indian astronomers were never good observers. They were at best mathematical manipulators. That's a very serious comment from Western Indologists, particularly the British Indologists. That way the French Indologists have been more sympathetic to what India has done, especially in the field of astronomy. And we as Indian workers in the field are indeed grateful to the French Indologists. But the British Indologists, the ones who wrote earlier, they were never that complimentary to India's contribution to mathematics. And incidentally, Professor Gavorgis made a reference to David Pingree. And Pingree and also his guru Neugebauer had a sort of bias against India's original contribution, especially in the field of astronomy. They always sought to convince us that Indians borrowed from either the Greek sources or the Babylonian sources. Well, we can't deny the possible influence of more Babylonian sources than the Greek sources so far as astronomy is concerned. Even if certain things were borrowed from the Western sources, it can't be denied that Indian astronomers improved on these things in a very big way. So much, in fact, I am going to show through some slides how the Indian computations yielded better results than Copernicus, let alone Ptolemy's. Because we are working in the field, we are familiar with it, we are computerizing all these algorithms, both Ptolemyean, Copernican, Keplerian, and our Indian system. And we are really feeling it is a very rewarding study, and we are publishing some papers here and there occasionally. Well, coming to these points proper, I told you that the Copernican theory, though it was a great breakthrough, actual coming to facts, that system of Copernicus did not work well, does not work well, because we are verifying eclipses and many recordings he makes of the observation. But it can't be denied that he was a very good observer. So also Ptolemy. In their Ptolemy's Almanacs, we see recordings of very important observations of eclipses, occultation of stars and planets, heliacal rising, setting, and so many interesting things. So we do respect these contributors for all the wonderful achievements they have made. But coming to Indian context, I told you that Gaṇeśa Daivajña and Nīlakaṇṭha Somayājī made great breakthroughs in the field of Indian astronomy. I will come to both of them one by one. Coming to Gaṇeśa Daivajña, his text called Grahalagavam has the epochal date of 1520 CE, March 19. In all these texts, as some of you might be knowing, the astronomical texts are of three genres. They are called Siddhantas, Tantras, and Karanas. Siddhantas are the big treatises where a lot of theory will be there and a large number of topics will be covered, including cosmology and the rest of it. Surya Siddhanta is an example. They are called Siddhantas. Siddhanta Shiromani of Bhaskaracharya, then Brahmasputa Siddhanta of Brahmagupta, and many other texts are there. But they are not useful for day-to-day computations. Then the second genre is called Tantra. Tantra is actually techniques or the algorithms, and Aryabhatiyam itself is the first Tantra that is available to us. And then the third genre, I am not going into details of all this, and incidentally, Professor Gevargi spoke of Mahayuga and things like that. No. Professor Valyathan spoke of Mahayuga and Yuga theory and all that, a bit of it. So, coming to that point a bit later, I may dwell on that. So, this Gaṇeśa Daivajña was a great contributor to the development of astronomy in this country. As is known to all students of spherical astronomy, spherical astronomy involves a good lot of spherical trigonometry. Just as we have the plane trigonometry, we have the spherical trigonometry, where three arcs from the sphere make a spherical triangle, and trigonometric relations are there, like the sine formula, cosine formula, and the rest of it. But actually using these trigonometric results was a big bugbear for the Panchanga makers. Like many other professions, we should realize that Panchanga making is also a family profession. My grandfather would be a Panchanga maker, my father would be one, I will be one, and perhaps my son will also be one. But not all of us are good astronomers, and not all of us are good mathematicians. So, suppose I am a dad, but still I have no other profession to follow except making Panchanga for the period of my life. So what am I to do? I am not very good at mathematics, and I am really scared of spherical trigonometry. So this was a great problem for the Panchanga makers. Of course, still life was made easier for them because tables, ready-made tables were their handwritten tables. Using them, if there is an error in the table, that would be perpetuated for centuries to come until somebody else corrects it. That is the practice, unfortunately. So what this Gaṇeśa Daivajña did, he was a very great astronomer and a mathematician. And in the morning, Professor Gevargi is referred to Gaṇeśa Daivajña's comment in his commentary on the Līlavati. It's called Buddhivilasan. The title itself is capturing. And in that he makes a very good analysis of various results of Līlavati. And he shows the importance of Upapatti, proof. So that's a significant contribution of Gaṇeśa Daivajña as far as the concept of proof is concerned. Now coming down to computations and the rest of it, I told you that this trigonometric formula etc. was very difficult for these Panchanga makers to follow. So what he did, I think he is the only man, only astronomer in the world who did this bold change in the computational process. What he did was, he totally dispensed with the trigonometric functions, sine and cosine. Any good student of mathematics would wonder, how on earth can we have spherical trigonometry or spherical astronomy without trigonometric ratios? He managed to do that. No sine, no cosine. He substituted the sine and cosine with algebraic approximation. And the algebraic approximation he has made is really wonderful. I think for the first time in the world history of mathematics, such a remarkable algebraic approximation to sine function is made, not by Gaṇeśa Daivajña. It was done much earlier in the 7th century by first Bhaskaracharya. We respect Bhaskara 1, though Bhaskara 2 is very popular. We respect Bhaskara 1, especially those of us who are interested in studying Kerala astronomy and the Aryabhatan school of astronomy, because only in Kerala the Aryabhatan school of astronomy is still followed. And I wonder why in the rest of India, Aryabhata was not at all followed, or the system of astronomy was not followed. Only in Kerala, they are rigorously following him. Lot of changes have been made, improvements have been made in procedures, parameters, observations and the rest of it. And we really congratulate the Kerala astronomers for all that they have given us. Now, so Bhaskara 1 plays a very pivotal role. Because of Bhaskara 1 only, we have been able to understand Aryabhata's mathematics and astronomy. Otherwise, by studying Aryabhatiyam only, it is not easy to follow, because though they are in the shloka form, they are very cryptic, very brief, because he meant it to be brief perhaps. It is only Bhaskara 1 in his commentary on the Aryabhatiya Bhashya, and his two independent works called Laghu Bhaskariyam and Mahabhaskariyam extensively details the procedures recommended by Aryabhata and also the parameters given by Aryabhata. So we are indeed grateful to him. So for the first time in the world history of mathematics, I will be glad if Professor Gevargi corrects me, that Bhaskara 1 gives the beautiful algebraic approximation to the sine function. And that approximation holds good even when the variable theta, the angle theta there is large. We as students of physics and mathematics, we have been using the usual approximation. When theta is small, sin theta is approximately theta, when theta is in radian. Even the pendulum problem and many such problems in applied mathematics, we have been using that. And it's a very bad approximation, as everyone of you should be knowing. When theta is large, large means even 40 degrees, 30 degrees like that, that formula breaks. That's why in simple pendulum we are advised to give small amplitude. That theta should be small, because in the derivation of the formula, they use the approximation sin theta is approximately theta, and theta is small and in radian. But here is a beautiful formula by Bhaskara 1, which holds good for any theta, any large theta you take, the error is minimal. In fact, on some other occasion we could or we would show the actual computations. One can tabulate using the two approximations and check how Bhaskara 1's formula is remarkably good. So that can be used even when theta is large. But unfortunately after Bhaskara 1, this formula, this approximation was not used by other astronomers until it was Bhaskara 2, and slightly before him it was Siddhanta Shekhara author Sripati Bhatta, the author of Siddhanta Shekhara, which was composed around 10th century. He for the first time uses this first Bhaskara's approximation in some cases only. And Bhaskara 2 virtually follows that, and he too in one or two contexts does use Bhaskara 1's formula. But this Gaṇeśa Daivajña did a great revolution in the field of our computational astronomy by totally ridding the subject of sine, cosine and all that, and replacing the sine with the beautiful approximation given by Bhaskara 1. All astronomical procedures are simplified, and to that extent the life of our Panchanga makers became easier. And today actually the most popular text for computations of Panchangas used in India, in the entire North Indian belt, in the entire Maharashtra and North Karnataka, in the districts of Dharwad and Belagavi. The text used is Grahalagavam of Gaṇeśa Daivajña, because it simplifies the whole thing. And the results are not bad. We have computed all of them, using all the chapters, eclipses and so many things. And they are coming out reasonably well with the simplified procedure. If you use modern procedures for solar eclipse, for example, those of you who have tried in the field of astronomy, you see it is quite complicated, and it takes enormous time to compute one solar eclipse using Besselian elements and all that. We are lovers of modern mathematics, and personally I have been programming all this using Besselian elements and all that. No doubt great accuracy will be there, but at what cost? How much time will I have taken? And in the absence of computer, how we have done it? And imagine even before calculators came, when we were students, we didn't have calculator or computer. We depended only on logarithmic tables. So you understand how much difficulty is there. And with the procedures recommended by Gaṇeśa Daivajña, it is simply a thrill for a worker in this field to get all the results very fast. Of course, they may not give very accurate result. An error of 2 or 3 minutes may come in the calculation of eclipses, such a thing happens. But we don't mind it, because we are not launching a rocket or anything to the moon. So this is about Gaṇeśa Daivajña. And I don't go into these details. Some of these just I will try to display, because there are lovers of physics and mathematics here who may like some of these things or can appreciate. Now in calculating the true positions of planets in modern astronomy, for example, if you take the sun or the moon, and if you want to have the geocentric true longitude of the sun or the moon, the procedure is, first the mean position is calculated. Even today it is the procedure, assuming that the body moves in a circular orbit with uniform angular velocity. Then, because we know that the bodies move in elliptical orbits, and the correction is applied, which is called the equation of the center, and that is called Mandapala in our Indian astronomy. Then for sun and moon, this is the major correction. And in modern astronomy, the gravitational terms are there, using which you correct the true position of the body after the main correction, namely the equation of the center. Then coming to the planets, Mars, Jupiter, etc. In modern astronomy, first here also for these planets, First the mean position is calculated, assuming that it goes around the sun in a circular orbit. Then a correction is applied for the elliptical orbit, which again is called the equation of the center. Correspondingly in Indian astronomy it is called Mandapala or Mandasamskara. Then the next step in modern astronomy, correcting for gravitational forces and all that, the next major step is to convert the true heliocentric position to true geocentric position, because we are observing from the Earth. So here in Indian astronomy, though they were not conversant or could not think of heliocentric model at all, still, because the results were not okay if they applied only one correction, by trial and error and by hypothesis and imagination, as Professor Balachandra was explaining in the morning, they sought to improve on the position of the planets by a second samskara or second correction, that is called Shigra samskara. That corresponds to, in modern astronomy, of converting from the true heliocentric to true geocentric. And very interestingly, the trigonometric formula we use in modern astronomy for transformation from heliocentric to geocentric is precisely the same as the Indians have been using for what is called Shigrapala. It is called Shigrapala, and except the small term called sin B or cos B, where B stands for the latitude of the planet, which is small because the inclinations of the planetary orbits with the ecliptic, they are generally small. For example, in the case of Jupiter, I remember it is approximately 1 degree 18 minutes, something like that. The most inclined orbit is of Mercury, that is about 7 degrees, and Mercury that way is really strange compared to other planets, and its eccentricity is also the largest next to Pluto. So leave alone that part for the time being. For the other planets, Mars, Saturn and Jupiter, the inclinations are very small. So the error incurred by ignoring this cos B or sin B is negligible. That explains why by Indian procedures, even to this day, we get reasonably good values for the longitude, latitude, etc. of the planets, as also of the sun and the moon. So this Gaṇeśa Daivajña simplified the whole thing by getting rid of sine and cosine. That is considered a great achievement. That is one thing. Then coming to observations, they were all good observers. And I told you at the beginning, it was the bias of the British Indologists who wrote earlier that Indians were never good observers, they were only good mathematical manipulators. That's a charge made against our Indian astronomers. But then the French Indologists corrected that attitude, and they were generally sympathetic to what Aryabhata and others had achieved. And present day Indologists, they are more level-headed comparatively, better informed, because one excuse is that these texts were not known to Europe those days, whether of Kerala origin or of the rest of India. They were all in Sanskrit. They were translated into European languages only after about 16th, 17th century onwards. So until then, they had reason not to know anything about India except what was carried from India by traders, Arabs and others, Jesuits and others to Europe. So that part is there, and Professor Bhavan has made a deep study of this, and it's interesting to read his books. So good amount of mathematical knowledge was transferred from India to European shores by the traders, by scholars, and the eastern part of Europe, a part of it was ruled by the Moods, the Muslim rulers. During that period, a good lot of transition was there. Now coming to the other astronomer, Nīlakaṇṭha Somayājī. Him we hold in great reverence because he made lot of innovations in the computations of astronomical procedures, both in theory and parameters. He was a very good observer. Not only he, almost every Indian astronomer was a good observer. Right from the first, one of the first Pancha-Siddhantikas, Bhavan left an anthology of the 5 Siddhantic systems. Among them, one is Vasishta Siddhanta. In Vasishta Siddhanta also it is recommended that you must follow only that procedure and computational arrangement which yields the correct result, which gives you the correct position of the planet or any heavenly body for that matter. They called it Druk-Ganita Aikya. Druk means observation, Ganita is computation, Aikya is their concurrence or concordance between computation and observation. This is an approach stressed by almost all Indian astronomers, starting with one of the most ancient astronomers, namely Vasishtha in his Vasishtha Siddhanta. Later astronomers have also stressed that, and Parameshwara, one of the really great astronomers from Kerala, again and again repeats this statement and makes the point that every astronomer should carry out actual observations and set right his procedures and parameters. And he says that what I am giving now in my text as parameters and procedures, they are not permanent always. They are true for only another 50 years or 100 years. In the future, astronomers should revise these parameters and procedures based on observations. He says, Kalantaretu samskaras chintyatam Gaṇeśa Kalantaretu, in course of time, samskara chintyatam. Samskara means improvement or corrections. Chintyatam is to be thought over by whom? Not by ordinary mortals like me, but by the best among mathematicians. Gaṇeśa. So they should revise these parameters, procedures, etc. And he was himself a very great astute observer. His Parama Shishya, his Shishya was his son Damodara, and Damodara's Shishya was Nīlakaṇṭha Somayājī. So for Nīlakaṇṭha Somayājī, Parameshwara was the grand teacher or the Paramaguru. And describing the scientific attitude of his Paramaguru Parameshwara Acharya, this man Nīlakaṇṭha says, my Paramaguru Parameshwara made astute observations for 55 long years by observing eclipses, planetary conjunctions, etc. Not only that, he critically examined them, pariksha, what does he say, samadruganitam karanam chakara. He says, panchashat varshakalam, 55 years, niriksha, that means observing, what? Grahana graha yogadishu, grahana and graha yogas, that is eclipses and planetary conjunctions. When we say planetary conjunctions, well, they include transits and occultations. But so far as transits of Venus or Mercury are concerned, they could not be observed those days because you can't directly observe the planet Mercury or Venus will be close to the Sun. And because of the brightness of the Sun, we can't observe either Venus or Mercury with naked eye. So only when telescopes came into use by reflected image of such a transit of Venus or Mercury, that could be observed. In fact, the first observed transit is said to be of Venus in 1631, I think, when Venus transit took place. And the same year Mercury transit also was there. And Kepler had already predicted correctly both the transits of Mercury and Venus. Unfortunately, the year before the transit took place, he passed away. But however, the later astronomers in Europe made the observations and have recorded. So 1631 Venus transit, and now recently we had this transit in 2012, Venus transit. So all these can be computed using these Indian procedures given by Indian astronomers, especially, starting almost with Aryabhatta, but they went on improving their procedures and parameters. So Graha Yoga Dishu, Graha Yoga includes, the conjunction of planets includes transits as well as lunar occultation of planets as well as stars. Same procedure you can adopt. So it says, Panchashat Varshakalam Niriksha Grahana Graha Yoga Dishu Pariksha. They did not observe just like amateur astronomers. Amateur astronomers are very good observers, very good astrophotographers and all that. But being a mathematician and a working astronomer, professional, he critically examined Pariksha, Samadruganitam Karanam Chakara. He made his Karana text, that is handbook. Karana means handbook, and I told you 3 genres are there. The last one is Karana Granthas. They are handbooks, just as we have laboratory manuals for physics, chemistry, etc. We have these Karanas. They are ready to use algorithms, and all these tables, sarinis, they are prepared using these Karana Granthas. Of course, depending upon different systems, whether Brahmaguptas or Bhaskaras or Gaṇeśa Daivajñas like that, corresponding tables are available to us. Okay, that is the main contributions of Copernicus, Gaṇeśa Daivajña, and coming to Nīlakaṇṭha Somayājī, I told you he was a very great theoretician as well as a very good observer and a very good mathematician. So in his text, Tantra Sangraha, which he composed in 1500 CE, In that, you see, he has elaborated on almost all the important astronomical phenomena and computations, procedures, etc. In that, the great breakthrough he made is truly remarkable, and personally I hold it superior to Copernicus. What does he say? You see, I don't go into details because that can be done somewhat boring to those of us who have had our length just a few minutes back. So I don't go into detail, but some of them I do highlight. Now, for example, this Nīlakaṇṭha Somayājī says he departs from the usual procedure of computing true positions of Mercury and Venus. The usual procedure in Indian astronomy for the major planets or superior planets, Mars, Jupiter and Saturn, is to find what is called the anomaly. There are two anomalies used. One is the anomaly from apogee or perigee. That is used for the equation of the center. For the second correction which I was mentioning, namely Shigra Samskara in Indian astronomy, there the anomaly used is the angular distance. It's not difficult to follow. It is the angular distance of the planet from the sun. How close is the planet to the sun? If the planet is in conjunction with the sun, that means if their mean longitudes are equal, then there will be no second correction at all. But if it departs from that apogee-perigee line, then you see there will have to be a correction. That is the procedure followed. And there you see what is done is, for the major or superior planets, the sun is taken at the center. That is called the Shigrocha. From there, the angle of departure or the anomaly is determined. Using that as the basic parameter, we find out the correction called Shigra Samskara. But the Indian usual procedure, for Mercury and Venus, a differential treatment was there. The sun is not taken as the point of center, the central point for anomaly. It is the sun is taken as the mean planet. It may look a bit odd. The sun's position itself is taken as mean Venus or mean Mercury, and there is a special point called Buddha Shigrocha and Shukra Shigrocha, which are the actual Shigrocha from which the anomaly is calculated, and that has been the practice since Aryabhata up to the period of Nīlakaṇṭha Somayājī. And this Nīlakaṇṭha finds fault with that system. He says, why are you giving this differential treatment? Even Venus and Mercury need the same treatment as the superior planet, taking the sun as the center for computing the anomaly. From the sun only you have to take the anomaly. This is a remarkable change introduced by Nīlakaṇṭha Somayājī, and this in theory or in principle amounts to telling you that all the planets, including Mercury and Venus, they go around the sun. And the sun himself, with the family of his planets, circumambulates the earth as observed from the earth. Mathematically, there is nothing wrong in that. All the rest of the planets, they go around the sun. And the sun himself appears to go around the earth for an observer on the earth. Due to relative motion, there is nothing wrong in it. Mathematically, it's not at all wrong. Physically, yes, we know that earth also is a planet. It's not the sun which goes around the earth, it is the other way. But mathematically speaking, it's not wrong at all. And this Nīlakaṇṭha, for the first time, gave that model of solar system. And that works better than our earlier procedures. And this is a remarkable contribution. Often it is called quasi-heliocentric model, and a very interesting paper appeared in the current science journal, I think in 1994. My own good friends in Madras, some of you must be knowing them, Dr. M.D. Srinivas, Dr. M.S. Sriram, and Ram Subramanian now in IIT Bombay. So these three people prepared that paper, and they had a lot of trouble in getting that paper published in the current science, for reasons best known to those who have been contributing papers to journals. And okay, I don't go into this too bit, but in this compound perhaps I should not speak out. So leave it on that part. The paper is really worthwhile, and it's a remarkable exposure of what the Kerala astronomer Nīlakaṇṭha had done to Indian astronomy. And remember, this Copernican model was nowhere in getting the results comparable to what a Nīlakaṇṭha's model could give. Not even Nīlakaṇṭha's, even before him, the Indian procedures were really good, except that the center of anomaly was shifted. That's all the difference made. But computations varied to a good extent. And since then, the Kerala astronomers have been following the Nīlakaṇṭha's model. And the same model, historically, it's interesting. The same model was adopted by Tycho Brahe later. Tycho Brahe came about 100 years after this Nīlakaṇṭha, and he was the master of Kepler. And Tycho was a very good observer, and very meticulous recordings of his observations he had made, and lot of description is given of the planetarium, the observatory he had, where the globe was with so many holes and calibration and all that. So very accurate recordings he had made. That helped Kepler to enunciate his three great laws. And critics tell us that if only Tycho had made an error of a couple of angular minutes in the position of Mars, Kepler would not have succeeded in enunciating his laws. So we are grateful to Tycho as much as to Kepler. Both were really great. And this Tycho Brahe refused to adopt this Copernican model, because he found that by adopting Copernican model, results were nowhere near the real ones. Where there's a lot of departure from observations he started getting. So he refused to accept the Copernican model, and he devised his own model, where again the planets go around the sun and the sun himself goes around the earth, exactly what Nīlakaṇṭha Somayājī had given 100 years earlier. And that model is now in the history of astronomy called the Tycho model, but actually it is Nīlakaṇṭha model, and we give credit to it. And Nīlakaṇṭha himself does not claim, and another great thing about our Indian mathematicians and astronomers is, none of them ever claimed he has done it for the first time, or it is his contribution. Even the otherwise generally considered as egoistic Brahmagupta also does not claim originality for what he has given in the solution of Varga Prakriti, or the second order indeterminate equations. Brahmagupta gets the credit of being the first in the world to give the general solution of a second order indeterminate equation. But Brahmagupta also does not claim it is his contribution. This has been the attitude of our Indian scientists all along in the past. And Nīlakaṇṭha also never says it is I who have been suggesting this. He says, my Paramaguru Parameshwara used to tell me this. So imagine, Parameshwara himself was in the 14th century, about 70 years earlier to this Nīlakaṇṭha. So even my Paramaguru was telling me this. And why the ancients did not understand it? That is his question. So it's a remarkable breakthrough in computational astronomy, also in theoretical model that was devised by this Nīlakaṇṭha Somayājī much before Tycho Brahe. And I told you that Copernican model does not really work, and he is totally confused. For example, he has to distinguish between heliocentric latitude and the geocentric latitude of a planet. Then he really fails at it. He is totally confused. Only a brief paragraph he reserves for that in his de-revolutionibus, and totally confusing the readers also. So whereas Nīlakaṇṭha in his Tantra Sangraha clearly distinguishes between the heliocentric latitude of a planet and also the geocentric latitude, that is the perpendicular distance from the ecliptic, how much it is and how the two are different, and what are the actual mathematical expressions for the heliocentric and geocentric latitudes. Latitude is called Vikshepa or Shara in Indian astronomy. So these are some remarkable things which we as students of science, I think, should appreciate, understand, and being Indians, I think we should respect it also, and communicate to our younger generation through our books and other things, textbooks. Otherwise, we are keeping our younger generation totally ignorant of what India has achieved. And there we should be very critical. We should not be fanatical and go on claiming not acceptable things as India's contribution. Only those genuinely tested, tried, and has been acknowledged by peer scientists elsewhere, that needs to be accepted. And mathematics and astronomy are two great fields where we can definitely feel proud of. This I was telling you. Now you say I don't go into details. This is called based on what is called the epicyclic theory. In the West, it was Ptolemy who systematized the epicyclic theory. Even before him, Hipparchus was there and others were there, but the writings are not available to us. In Ptolemy's Almagest, we are given good treatment of this epicyclic theory. And there you see, for example, for a planet, take the sun or the moon. We imagine, as I said earlier, the body moves in a circular orbit that is called the deferent circle. Then, at every point on the circumference, you have to imagine a circle that's called epicycle. And the center of that is the mean position of the body. The actual planet moves on that small circle called epicycle. And in Greek theory, or Ptolemaic theory, two epicycles are recommended, which correspond to what I said, equation of center, the other part, the second correction. In Indian astronomy also, they advocated using two epicycles and given the circumferences of these cycles. They are different for different bodies. That's what I am speaking of here. The periphery, that is the circumference of the epicycles, they are given in degrees, not the linear unit, because they are considering the ratio of the circumference of the epicycle to the big circle or the mean circle or the different circle as it is called, which is taken as 360 degrees. So the ratio is taken, and you agree with us that ratio of circumferences is also at a stop. Okay, sorry. Sorry, we go on talking, I keep on talking. Okay, the ratio of the circumferences is also the ratio of radii. So in Western astronomy they speak of radius of epicycle. Here they speak of periphery or the circumference. So we have recommended, based on modern computations, the epicyclic dimensions for the various heavenly bodies, and these are the ones based on, of course, in modern astronomy you don't need to have epicycles. Today we know that the planets move in elliptical orbit, but suppose there is a great need, because I am not going to explain the importance of it. See, we are living in a traditional society, whether for good or bad, and in our households we have been using panchangas for our festivals and even marriages and so many things. Now the panchangas which are in vogue today, they are all defective. Scientifically they are not correct, because they are based on texts composed some 500 or 1000 years ago. So they can't be expected to be very correct now. But they are not altogether off the mark either. So they need improvement or revision. And that effort has to be done by those who are familiar with both traditional astronomy and modern positional astronomy. Only such people can take up the task. And some of us are involved in that. And we are suggesting, without ruining the framework of the traditional astronomy, without going into ellipse and other theory, going back to our own traditional system, epicyclic theory, it works reasonably well. Only you have to change the dimensions of the epicycles and also the angular velocity of the planets, because they have changed. Today we know that the planetary orbits are becoming bigger and bigger. When the orbits become enlarging, then the rates of motion will be slower. When the rates of motion of the sun or the moon, as seen from the earth, are varying or changing every year or over a century, say, then the length of the nakshatra, length of the tithi, etc. also go on changing. So a lot of discussion has been there. Traditionalists on one side and the reformists on the other side. But to be scientific, we have to reform our Panchanga system. So the need to, without destroying our traditional system, there is nothing seriously wrong with it. Only it needs improvement. Just as our Indian medicine needs modern research, modern trials and things like that. So there is no point in discarding Ayurveda or Unani, any of such systems. They are functional, they are operative. So also is our astronomy operative. We are suggesting, recommending some of the revision of parameters, and some progress is going on in that direction. With this I conclude. Go ahead, much else to cover. Sorry, I couldn't. So thank you.